All right. In this module, we're going to start to look at the mechanical properties of polymers. So this is actually material that is in the mechanical properties chapter, so not chapter 4 on polymers. And then we'll also talk about viscoelasticity in the following module. All right. So when we look at the mechanical properties of polymers, we tend to look at the stress strain curve for a tensile test, just like we did with metals and some ceramics. And we can kind of divide their behavior into three main categories. So we have brittle polymers, where just like brittle ceramics and brittle metals, it doesn't exhibit a large degree of strain or plastic deformation. And so you can kind of just see a linear elastic behavior. So that's just elastic, and then it fractures with very little change in shape. We also have plastic. So here, when we talk about plastic, we're talking about plastic deformation. So that's why I always refer to polymers as polymers, not as plastics, because not all polymers exhibit plastic behavior where they have a substantial amount of plastic deformation. And so the blue curve is a good example there, where it kind of yields, and then there's plastic deformation, non-linear, and then it fractures after substantial strain. And then the last category are elastomers. And this is where it looks nonlinear, but all of this is actually elastic behavior. It's just nonlinear elastic behavior. So the gummy experiment that I showed early on in the mechanical properties chapter was an elastomer, and it had nonlinear elasticity. And so that's the example here. So even though it extends up to 750, so about 750% of its original shape, that is all elastic, and so it'll go back to its original shape afterwards. So that's the important distinction with elastomers. And so these are things like rubber bands and rubbers and things like that. So a couple key notes in terms of comparing this to ceramics and polymer and metals. So the elastic modulus is well under that of metals. We're talking about in the hundreds for metals, 100 gigapascals. So we're definitely talking less than that. Fracture strengths are also about 10% of those of metals. But the deformation strains, so the amount of plastic deformation, can be over 1,000, whereas metals tend to be 10% or less, or something in that ballpark. So these are kind of illustrate some of the similar characteristics, but also some of the dissimilar characteristics of polymers. All right, so let's look at brittle polymers and see what results from that behavior. So when we think of brittle, we're tending to think of networked and heavily cross-linked polymers. So those are the ones that are predominantly amorphous. So glass-like behavior, right, is brittle. So these are amorphous, they're networked, heavily cross-linked polymers. And so they're going to exhibit this red behavior where it's elastic, but then it rebounds. And so we have brittle fracture. If we're talking about an aligned cross-linked polymer, so something like this, where we have those cross-links in between lines, what's happening as we strain that is we're stretching the bonds in the polymer, and you can see that it's longer now, and effectively at fracture, we're breaking apart those covalent bonds. And so there is a fair degree of strength here, but very little plastic deformation, because once we break those covalent bonds, the material breaks without much deformation. So all of that's elastic. And we can also think of it in terms of networked in the same way. All of these networks are connected by covalent bonds, and so when we stretch them, we're stretching covalent bonds, but at some point it will just fracture with no plastic deformation, because essentially all we can do is break those covalent bonds. We can't have slip like we did in metals, and then because all these individual repeat units are connected by strong covalent bonds. So that's what we would expect from a brittle material. So now let's look at semicrystalline polymers. And these are the ones that tend to exhibit plastic deformation. So they're the ones in blue here. And what we see there is that this area right here is the onset of necking, just like it was in metals. The what's happening is a bit different, but we still have a phenomenon similar to necking. And then we have substantial plastic deformation before failure. And we can do the reload, unload, reload, just like we did before, which can change the strength if there is that strain hardening effect. So let's look at it on the sort of structural level. So undeformed, if we make a tensile bar out of it, we're going to have crystalline regions, you can see, and they're connected to non-crystalline or amorphous regions in between. And so when we stretch them, we're actually stretching the amorphous regions, which are easy to move. So up here, right before necking, we're moving all the amorphous regions. And then at necking, this is where the crystalline regions are aligned. And basically, the amorphous region has extended kind of as much as it can, right? So the crystalline regions are aligned, the amorphous regions rearranged as much as it can, and so after that, if we're at this point here, those crystalline blocks start to segment apart, and so you get regions where they're having to kind of break apart the larger crystals. And so that's continuing to occur. And so basically, the whole process here is kind of aligning everything and pulling apart and basically making these chains as long as they possibly can. And eventually, at failure, you formed all of these fibers from these crystalline blocks that have come apart, and they basically start to break. And so that's when the covalent bonds start to break within the chain. And that's why the strength tends to go back up a little bit towards this region. But these types of failures, they're indicative. You can see them because it becomes very fibular. So you can see, basically almost see little fibers coming out at the end, and it's very fiber-like. It almost looks like there's little fibers within your material, but it's just the alignment of these chains into specific kind of fiber regions. So for these types of plastic polymers, when you draw them like this, and that's just the process of reducing the diameter like a wire, it increases the strength typically, but decreases the ductility. So this is very much the same as strain hardening in metals. So what you're doing here, though, is you're stretching the polymer and you're aligning the chains in the stretched direction. So it increases the elastic modulus, it increases the tensile strength, but it decreases the ductility. And just like metals, we can actually anneal after this drawing process, and that will decrease the alignment and reverse the processes that we just saw in drawing. So decrease the modulus and strength, and increase or enhance the the percent elasticity, or sorry, percent elongation, so the ductility. So this is very much the same as cold work and annealing in metals, but obviously the blocks here, this is polymer chains and not polycrystalline material. All right, so the last material, elastomers, this is that exhibits that large nonlinear elasticity, and the way we can think about these are quite a bit different than the brittle and the plastic behavior. What we typically have here is something that looks kind of like this. So they're kind of amorphous chains, and there tends to be some cross-linking. So a small amount of cross-linking here. So they're very kind of chaotic, disordered chains that are amorphous. They're kinked, and they're also cross-linked. So what happens is, as you stretch this, those chains tend to align. And so the chains tend to align, but you still have that cross-linking. And so they become straighter, but they're still cross-linked. And so if you catch it before it breaks, then if you remove the force, it will go back to its original shape, because those cross-linkings basically tie it to that pre-existing shape. And so they're very chaotic here. But if you don't, it'll break, but it'll still return to its initial shape. So elastomers are quite a bit different than what we expect with the other classes of material. And so here's actually a tensile test of a rubber band. So it's hooked up to a tensile test with these hooks. And you can see that it stretches quite a bit compared to its normal shape. And so over here you have this kind of shape, and then as it stretches out, you had that lengthened shape, but it'll go back to its original shape. All right, so let's talk about some of the general characteristics and effects of the mechanical properties. So temperature becomes more important in polymers because polymers have very low melting temperatures, right? So if you go from room temperature to minor increases or decreases of room temperature, right, those are much higher percentages of the material's melting temperature. So temperature is a very big effect. And so here we're looking at PMMA, polymethyl methacrylate. It's also known as plexiglass. It's a semicrystalline material. And if we increase the temperature, we see at the really low temperatures, it's very brittle. And then as we increase the temperature, it becomes more and more plastic. So you see that the strength's gone down, but we have some plasticity, even more so. And then if we go up to the high temperature, you can see it acts like one of those semicrystalline materials. So basically, if we want to think about it in terms of decreasing temperature, then it increases the modulus, so the slope here. It increases the strength, so going up here, it's much higher strength than these, but it decreases the the elongation. So this one is very high, so 1.3. All of these are lower than 0.1, so drastically decreases the elongation. So, and the reason this is for these chain type polymers is that increased temperature allows for that increased chain mobility that we've talked about relative to the glass transition, and therefore increases ductility but decreases those others because that's resistance to those effects. Also, we have to think about the way that we test the material. And so how quickly we pull or strain the material is known as the strain rate. And this has a similar effect but opposite to temperature, because the faster that we test it, the less time we're allowing for chain motion. So the increased strain rate limits chain motion, right? If you think about it, if you pull it really fast, then we don't allow time for those chains to move and to adjust to the higher forces and strain. So what we see is that with increasing strain rate, it has the same effects as decreasing temperature. So here's kind of an illustration of that. So a lower strain rate, you can see, has slightly more strain or elongation, but lower strength and lower modulus. However, if we increase the strain rate, it makes it stronger, but it also can make it more brittle or less elongation. So increasing strain rate has the same effect as decreasing temperature because it's the same idea with limiting chain motion.